What I hope to do in this video is derive a formula for the sum of a finite geometric series. And right here is a finite geometric series. I start with some first term a. Notice I wrote it as a times r to the 0, but r to the 0 for any r, we're assuming r is non-zero, this is going to be 1 right over here. So our first term is going to be a, and then each successive term is the previous term times our common ratio, times r. So a times r is a times r to the first. That times r is a r squared, on and on, all the way until we go a times r to the n. This is a finite series right over here. So let's just define this series. Let's just define this. I'll use this, the letter s sub n, as being equal to this, all of this business right over here. Now let me multiply s sub n times our common ratio. So let me write this right over here. So let's say we have r the same color as our previous r times s sub n, r times s sub n, and what is that going to be equal to? Well, we're just going to multiply each term here by r. And we could even multiply this thing by r if we want as well. This would now be the sum from k equals 0 to n of a times r. But now instead of r to the k, we're now multiplying each of these terms times r again. So it's going to be to the k plus 1, to the k plus 1 power. Or, and it's a little easier to conceptualize right over here, let's just multiply each of these terms times r. So a times r to the 0 times r is going to be ar to the first power. So that's going to be a times r to the first power. Let me write that down, a times r to the first power, or just a times r, because obviously r to the first is just r. And then plus, let's multiply this term times r. So plus a times r squared, a times r squared. And we'll just keep on going. We'll just keep on going until we're going to get all the way to a times r to the n plus 1. So let me write it like this. So we're going to go to plus, and typically you'd only write 3 dots. I went overboard with my dots, so let me do it. Dot, dot, dot. So plus a times r to the n times r to the n plus a times r to the n plus 1. R to the n plus 1. So notice I just took each of these terms and multiplied them by r. You see that right over here. Multiply by r, get that term. Multiply by r, get that term. And then I don't show the other ones multiplied by r, but all the way to multiply this one by r, and you get this term right over here. Now what I want to do is something really neat, and this is one of my favorite derivations in all of mathematics, because you're able to do something pretty neat at this stage. What happens if I were to subtract r times s sub n from s sub n? So let's think about that. Well, over here, we would just get s sub n minus r times s sub n minus r times s sub n. So notice, all I'm doing is I'm starting with this, and I'm subtracting both sides, the same thing from both sides of the equation. On the left-hand side, I'm subtracting r times s sub n. And on the right-hand side, from this, I'm going to subtract all of this. So what do we get on the right-hand side? So this is going to be equal to, and I'm going to ignore this for now, because what we really care about is this business. So a times r, what I'm going to do is I'm just going to cancel out all of the terms that have the same degree. So for example, so a times r to the 0, there's no other r to the 0 term here, so we're just going to have that a times r to the 0, or I could just write that as a, obviously, r to the 0 is going to be 1. So I'll just write that as a, that's that right over there. And then we have a times r to the first power minus r to the first power. Well, that's just going to cancel out. These are going to cancel out. They're going to keep canceling out. They're going to keep canceling out all the way until all we have left over is this, and there's nothing to subtract this from. We have no a times r to the n plus 1 power up here, so we're just going to subtract it. So minus a times r to the n plus 1. A times r to the n plus 1 power. To the n plus 1 power. And now we can just solve for our sum. Remember, that's the whole point of this video to begin with, to try to derive a formula for this sum. So let's factor out s sub n here. So this is S sub n times 1 minus r, 1 minus r, is equal to this right over here. It's equal to the first term minus the first term times r to the n plus 1. So one more power times the number of terms in our original sum. So let's do that. Times r to the n plus 1 power. N plus 1 power. And so to solve for s sub n, we just have to divide both sides by 1 minus r. Divide both sides by 1 minus r. 1 minus r. And so we are left with, if we assume r is not equal to 1 in this case, we are left with s sub n is equal to a minus a times r. I'm just rewriting what I have up here. R to the n plus 1, r to the n plus 1 over 1 minus r. Over 1 minus r. And you say, hey, Sal, well, why is this at all interesting? Why is this useful? Well, let's actually apply this. Let's actually apply this formula that we just finished deriving. Let's say that we have a geometric series. So let's say our first term is, I don't know, let's say our first term is 3, and it's 3 times, I'll do the same colors as I was doing before. It is 3 times 1 half, 3 times 1 half to the kth power. And we're going to start at k equals 0 all the way to, I don't know, k equals 100. And just to visualize what this looks like, this is going to be equal to, the first term is just going to be 3 times 1 half to the 0 power is just 3. So our first term is 3, as was intended. So our first term is 3 plus 3 times 1 half to the first power now. This is 1 half to the 3 times 1 half to the 0th power. Now 3 times 1 half to the first power. 3 times 1 half. I could write a first power there if I like. And then plus 3 times 1 half squared. 1 half squared. And we'll just keep on going. We'll just keep on going all the way. I'll do it right over here. Plus, we're going to keep on going all the way until we get to 3 times 1 half to the 100th power. Times 1 half to the 100th power. Now you can imagine, you could probably calculate this with a calculator, but it would get very, very hard and would be very, very time consuming to add up these 101 terms right over here. Instead, we can apply this formula. So this sum right over here is going to be equal to, if we were to add it up, it's going to be equal to our first term, which is 3. It's going to be equal to 3 minus 3 times 1 half times 1 half. 1 half is our common ratio here, times 1 half to the n plus 1. Well, n is 100, so it's to the 101 power. 101 power. All of that over 1 minus 1 half. And now this is much easier, it would be hard to do it in your head, but this is much easier to type into a calculator and actually get a reasonable answer. So let's actually do that, just so it'll feel satisfying. So let's clear this. So it's going to be 3 minus 3 times, I could write 1 half is 0.5 to the 101 power. 101 power. Did I get the numerator? 3 minus 3 times 0.5 to the 101 power divided by, well, 1 minus 1 half is just 1 half. So it's just going to be divided by 1 half or divided by 0.5. And we get 6. We get 6. And it's not going to be exactly 6. And we're going to see that when we take the infinite sum, that's going to be exactly 6, but it's going to be pretty darn close. We're hitting up against the precision of the calculator. So based on the precision of the calculator we get, it's going to be pretty close to 6. Pretty close to 6.